We're going to be covering a lot of different topics in this video, but let's start with our magnetic flux density. So this is sort of similar to our electric flux density. So remember, with electric fields, we talked about an electric flux density D, which was equal to epsilon times our electric field intensity E. And so our magnetic flux density is going to be similar. So up here at the top, I've gone ahead and given us the units. So it'll typically be reported in either Webers per square meter or in Teslas. And so the relationship between this magnetic flux density and our magnetic field intensity is B equals mu naught times H. And where this mu naught is our permeability of free space. And so that value is 4 pi times 10 to the minus 7th henries per meter. And again, that's our permeability of free space. And so just like we started out with only dealing with free space with our electric flux density, and we came back and we added in sort of a relative permeativity, epsilon sub r, we can update this later on as well and add a mu sub r, or a relative permeability of a material. Okay, so now that we have this magnetic flux density, we can define magnetic flux through some surface. So let's talk about magnetic flux through a surface. And so remember, this was sort of the same approach we took with our electric flux density, and using our Gauss's law, we were able to find an important equation. We're kind of going to follow the same path here. So magnetic flux through a surface, which is going to be in units of Webers, so the per square meter is going to cancel out in our B, is going to be psi is equal to the integral over the surface of B dot ds, where ds is again just going to be pointing outward. If our surface is enclosed in a volume, that ds is pointing outward from the volume. So we can also define magnetic flux lines. So as I said, we're kind of jumping and covering a lot of different topics in this video. So let's next move on to our magnetic flux lines. We're kind of going to come back and connect all of this together here in a little bit. So of course these are going to be similar to our electric flux lines, and what these are is just going to be a path where our B or H is tangential at every point. So B, and really because B and H for a uniform material are just going to be related by that proportionality constant of mu naught. So we can say B or H is tangential at every point. So let's say, for instance, we have some current in a wire, and so here's our wire, and let's say our current is coming out, so we get something like this. Well, we know we're going to have from the right hand rule an H field and therefore a B field that is sort of going counterclockwise around that wire. So let's go ahead and add in our flux lines then. So we're just drawing this path where our H or our B is going to be tangential at every point. So we'd have our path going in this direction, and so we could draw another one further out, and so we could draw however many flux lines we wanted. So a couple other ways that we can think about this, and then a couple important things to note, is we can also think of these magnetic flux lines as a line along which a magnetic compass would align itself. So say we had a magnetic compass with a north and a south pole. If we put it on that magnetic flux line, it's going to align such that the north pole is in the direction that this flux is pointing, and our south pole is in the opposite direction. So it's kind of difficult to see, but I've tried to draw that arrow pointing upward. So that's another way that we can think about our flux lines. So one big difference that we see if we compare this to our electric flux lines, so let's just kind of to go back and think about our electric flux lines. The simplest case, we said, what if we have a point charge? So maybe I have some plus Q here. So in that case, we said our electric flux lines are emanating radially from this point charge. So we had something like this. And so that's going to be going in all directions. So I'm not necessarily doing a great job of drawing that symmetrically. But we have these electric flux lines. So this would be our electric flux. So we see that they're going sort of in all directions. They have sort of a starting point at Q and an ending point towards negative infinity. The big difference here is that our magnetic flux lines are always going to be closed. And so we see that represented by these closed circles. And that's always going to be the case. Not necessarily that they're circles, but our magnetic flux lines are always closed. And so what that's saying is basically they have no beginning and no end. We'll talk about the implications of that here in a second. So one thing that implies then is that we cannot have an isolated magnetic charge, or in other words, a magnetic pole. So let's just say this down here. So cannot have an isolated magnetic charge or magnetic pole. So you can see that represented both ways. And so the idea is, of course, with this point charge, we're able to get this isolated Q, but we can't do that with our magnetic charge, so to speak. And we can consider that, if we had a bar magnet like this is sort of the classic example. And let's say we have our north pole and our south pole for our magnet. Well, what happens if we say, okay, well, north's on the top, south's on the bottom, let me just cut this guy in half. And you'd think, I have now a north pole and a south pole. Well, it turns out you're just going to get two bar magnets, and I realize this isn't the same scale, but you're going to end up with two bar magnets, and each of them are going to have a north and south pole. And so you can keep subdividing that, and you're always going to have a north and south pole. So that's the big difference between our magnetic flux lines and our electric flux lines. Now, as a consequence to that, that means that the total magnetic flux through a closed surface has to be zero. So let's come back here and say this was just sort of general magnetic flux through a surface. But now if we're talking about a closed surface, so magnetic flux through a closed surface has to be zero. So must be zero. So we can write that in terms of an equation. So we can say the integral around a closed surface of B dot ds, because we know that's our general equation for a magnetic flux, is equal to 0. Okay? And so sometimes you'll hear this referred to as the law of conservation of magnetic flux. So law of conservation of magnetic flux. And so it's kind of analogous to Gauss's law. So as I said, sort of this whole process that we were talking about here in terms of defining our magnetic flux density and then magnetic flux was the same sort of setup we took with Gauss's law, and then that ultimately ended in saying that the flux through some surface is equal to the charge enclosed. And in this case, instead of having the charge enclosed, we have the total flux through a closed surface is 0. And the reason for that is because, of course, we can't subdivide, we can't get just the north or just the south pole. We always have both, or some multiple of both. So basically that's saying if for whatever reason we couldn't isolate a positive point charge, but it always came with a negative point charge as well, in which case, of course, the total Q enclosed would be 0. So it's the same sort of idea, just sort of paralleled with our magnetic poles. So our magnetic flux through a closed surface is always going to be 0. Another way that we could sort of think about that pictorially is, let me just sort of draw an arbitrary closed surface here. So this is some closed surface. Now we know our magnetic flux lines are closed, so let's say, maybe we have some magnetic field here, and actually let me go to this darker one. So we have some magnetic flux that's coming through this surface. It's inside this surface here, but we know that this has to be a closed path. So from when this comes back out of the surface on the bottom, it ultimately has to be looping back around to where it started from. So because of that, everything that is going in at this point here has to be coming out at this point down here. And so we could draw any number of flux lines going through, various degrees. So maybe this one comes in here, it goes through, comes out the bottom. But again, it's a closed path, so it's going to have to come back and loop back on itself. So because of that, everything that is going in is also coming out. So we have a net magnetic flux in our closed surface of 0. Okay, so the final thing we want to do then in this video is we want to apply our divergence theorem to this equation. So from this, let's apply our divergence theorem. So that was back in our vector calculus. And so what that says is that we have this closed surface integral of b dot ds, and we can relate that to a volume integral. So we can say that's equal to the volume integral of the divergence of b times dv. And because we know that surface integral is 0, we know that this volume integral also has to be equal to 0. And so of course, remember, just like when we've applied this in the past, this volume corresponds to the volume enclosed by the closed surface S. Okay, so now what we can do is we can say, well, if that volume integral is equal to 0, then the integrand has to be 0. So that means this integrand in here must be 0, and we can finally complete our Maxwell's equations by saying that the divergence of B is equal to 0. So this is our fourth Maxwell equation. And so what this is implying then, if we think back to our basic definition of divergence, is it's implying that our magnetostatic fields have no sources or sinks. So it implies our magnetostatic fields have no sources or sinks. And again, this is all sort of related back to that idea of we can't have a magnetic monopole. We have to have the north and south together. So one important thing to note is that we've only been looking at these Maxwell's equations for static electric and magnetic fields. So these are for static, so very important distinction. There are slight adjustments that need to be made if we're talking about fields that are varying over time, but unfortunately we're not going to have time to get into that. But again, these are for static electric and magnetic fields. And so there is a very nice summary on page 319 in the textbook. So not page again. So on that page 319, table 7.2 has a good summary of all four of Maxwell's equations, the integral and the differential form. And so as they point out, depending on the problem, sometimes the integral form is appropriate, sometimes the differential or point form is appropriate. But either way, that's a good reference to have, particularly as you're making your note sheets and preparing for exams.